We are going to study in these lectures. We are studying power devices and circuits. This is the broad field of power electronics. You studied a lot of electronics till now, analog, digital, systems. In many cases, you studied the flow of information. You have a signal. You started with analog electronics, studying the input signal and how you can amplify it. The typical processing chain that you studied is the following. There is a signal somewhere, a source of information. Then you have an input interface that is a transducer or something like that. Then you have signal conditioning. Signal conditioning, that is some differential amplifier to take the signal and to remove the noise or change the voltage, reference voltage, something like that. Then you have a broad stage of signal processing. The signal processing stage is what you studied the most, that is amplification, filtering, digital circuits for modifying, storing, and modifying the signal. Then there is something to provide the signal to the output and an output interface and then the load. As you can see, you studied the processing chain for the signal. However, in this entire process, we completely forgot something that is very important. That is the energy that you need for this kind of processing. In every portion of this processing chain, you need some energy to activate the processing. In this slide, you schematically see in these green lines that are the energy sources. There can be more than one energy source. And this is the flow of energy. You need energy everywhere, and maybe a big portion of this energy is in this stage, the output stage and the interface, when you need the energy to drive the load. This load can be something that needs a lot of energy, can be a motor, can be a loudspeaker, can be something that is physically big and needs energy to be activated. Not every kind of energy is good for these circuits. You need a particular voltage, a particular amount of current, a particularly stable current or voltage. This means that these energy sources here are different and need to be designed for the particular application. The key aspect of this processing chain with the energy that is provided by the sources is the efficiency. You not only want a particular voltage, a particular amount of current, but you also want to provide this current and this voltage without wasting a lot of energy. No one wants a circuit that uses, in order to provide 10 watts to the load, dissipates 20 watts. This is a problem not only for the power dissipation, for the cost of the energy, let's say the amount of the bill that you have to pay for this extra energy. The real problem is also the heating. When you dissipate this amount of energy, your circuits will become hot and the reliability is destroyed. In a power electronics system, the typical processing chain will be something like this. You will have a power supply that is not regulated. The raw source of energy. Then you have some kind of filtering to generate some kind of constant voltage. Then you have the power circuits, that is the real circuits that controls the energy output and output filtering, and finally the load, that is the circuit, the system that will use the energy. In this circuit, you will have a number of devices, active devices, transistors, diodes, MOSFETs. These are not conventional devices. These are particular devices that are designed in order to sustain and handle a large amount of power. They are conventionally named power semiconductor devices. And this is also something that we will study. The power devices are the core of these power circuits. Most of the power circuits are basically determined, their performances are driven by the power devices. When we here write load, we can intend a number of very different things. Motors, actuators, ovens, lamps, electronic system supply, displays, antennas, spark plugs, pumps, automotive. There are a lot of applications. Every electronic system needs a power supply. This means that what we are studying now is widespread and needed every time you design a circuit. We will not go very in depth in the circuits, and actually our circuits will not have any kind of feedback. But in a real system, it must be said that there will always be some kind of feedback. Because you have a variable, not stable power supply, and also a variable, not stable load. And this means that you need some kind of control, feed forward or feedback, that controls the power supply, controls what is happening to the load, and with the signal processing chain and some drivers, modifies the behavior of the power circuits in order to maintain the system stable. What can happen? This could be, as an example, this is the mains, the power supply from the 220 volts that we have. This is the load. This can be our phone, cellular phone that we want to charge. What can happen? This voltage can change. You don't want to change the voltage here. Or we can plug or unplug our cell phone. And if we plug or unplug the cell phone, we don't want to maintain constant current that we are driving on the output, because if there is no load, this current cannot go anywhere. Or maybe that for an error, we can short circuit the output. We can short circuit the load while trying to plug the cell phone. And in this case, you don't want that the current goes to the maximum possible, because you are destroying the power circuit. Hence, you need feedback and feed forward in order to control the circuit. But we will not study these aspects of the power circuits. Where power electronics is used? Almost anywhere, everywhere. People, portable electronics, tablet, notebooks, smartphone, clocks, health monitoring, very important now, personal communications, buildings, heating. There is a lot, air conditioning, fan, refrigeration. There has been in the past a lot of advertisement about the higher efficiency for inverter air conditioning. What is changing is the kind of power electronics that we use. Lighting, we know everything about the efficiency of these lights, and you have the lamp ballast. You need the electronic circuits that do this kind of control. You need to change the voltage. the old incantation lights were directly plugged to the mains, but this low voltage, this is not a LED, but if you use LED, you need a low voltage controlled low voltage source to drive these kind of lights, and the efficiency is extremely important, obviously. In the industry, you use a lot of energy. Electric motors, pumps, arc and induction furnaces, these are huge powers. Welding, lasers, transport, robot, belts, conveyor, these are systems that need a lot of electrical energy that must be controlled and must be efficiently provided. Automotive and railways, obviously, traction. The trains are driven by electricity, and the power circuits into the trains are extremely important, very big, a lot of power there. Battery chargers, drive control, safety communications. Now the cars are full of electronics. Aerospace, airplanes, control, maneuvering, satellites, and space supply. Power distribution and generation. And this is the highest amount of power that we have. Photovoltaic and wind generation, fuel cells, high voltage DC supplies, static var compensation, accumulators, medium voltage power distribution. These are very high power applications. Among these large and huge amount of applications, how can we classify them? We are talking about power. Everybody knows that power is the multiplication of voltage multiplied by the current. So the first classification could be the power. However, as we will see immediately, we cannot actually trade off voltage for current for a given amount of power. Usually the voltage is fixed and then it comes the current. This means that we can classify the applications as a function of the voltage and the current separately. It is clear that mostly you have this trend that if the voltage increases, also the current increases, but the application can be more or less classified like this. There are some applications like displays that have low current and high voltage, but and also power supplies that have low voltage and a lot of current. Think of the power supplies for our computers, desktop computers, not this one, and that the voltage is around 100, 200 volts, and you have 200, 300 volts, and you have 100, 200, 300 watts. And then telecommunication, lamp ballast, automation, motor control drives, and this is AC voltage, power energy transfer at very high voltages, 10,000 volts and more. We reach million volts, and the current that is in the order of thousands of amperes. Voltage and current, as previously said, depends on the application. You cannot change that. If you have an application that is connected to the mains, the voltage is 230 volts, and you cannot change that. If you want to change the power, you need to change the current. And there are many other applications like this. If you are operating on a battery, the battery has a fixed voltage, more or less. It will change when it's charged or is discharging. But in the end, if you want to change the current, the power, you need to change the current. You cannot change the voltage. Another possible application, way of classifying the power electronics applications, is the operating frequency. This is new for us. We know that power is voltage multiplied by current, and what is this operating frequency now? We will see very shortly that power circuits and modern applications operate the power semiconductor devices in a particular way, that is class D operation. These devices are switched on and off. Do not operate in the middle. Do not operate in the linear range of operation. And this switching on and off happens to a certain frequency, and it can be easily demonstrated that higher switching frequency means usually better efficiency, better performances, smaller devices, smaller circuit, and less cost, and etc. This means that the designers usually tend to maximize the switching frequency. The limits are the devices, and we will see later the power dissipation. However, for a very fundamental physics motivation, big circuits, big devices tend to switch slower. This is true for mechanical systems. If you have a very big system, the typical oscillation frequency will be smaller, and small systems will move much faster. And more or less the same happens for power devices. Power devices for low power application can be small, can be designed in a particular way to be very fast and switch at very high frequencies. If you have higher power, and very high power, you need to use different devices. These devices will be designed differently, but will be bigger, just bigger in terms of their size. And they will switch at much lower frequency. This means that we can classify the applications also in terms of the switching frequency. And in this graph, you can see that on the y-axis in log scale we have the power, and on the x-axis we have the switching frequency. We will not deal with telecommunication and microwaves. These are very high frequency applications that are also classified as power, because the microwave oven provides a certain amount of power to our food. Otherwise, it cannot cook it. It is clear, but we are not going to study this. But talking about these slower operating frequency applications, we can see that higher power usually comes with smaller and slower switching frequency. Which are the typical switching frequency for our devices? You come from analog electronics and digital circuits, and you are used to see your notebook and processors that switch at some gigahertz, and you think that 1 megahertz is a very slow frequency. And this is true for signal MOSFETs, signal devices, digital circuits. But in our circuits, we are talking about power. The power increases, and this switching frequency is not possible anymore. And this means that typical switching frequency are kilohertz for a medium power device, medium power application, that can reach 100 kilohertz for very high switching frequency applications. But if you go to very high power, you can easily go to 100 hertz switching frequency. This means that in terms of switching frequency, operating frequency, these circuits will be very, very slow if we compare them with digital circuits. But obviously there is no other kind of comparison, because digital circuits can be so fast because they use the trick that they need just to process the information. And reducing the energy that is stored in a single bit of information, reducing the supply voltage, making the single bit MOSFET very small, this can reduce the amount of energy, and this means that we can switch at higher frequencies. This is the physics that is behind the scaling theory. But it only works because we can scale everything. We scale the amount of energy for a single bit, we scale the load, we scale the other circuits. When we go with power electronics, we cannot scale everything. Because in the end, if you need to drive an engine, that engine must be big as you need it. If you want to make a train work, this train is as big as it can be. You cannot make it smaller. And this means that the energy is much larger, and the switching frequency can be very, very small. I told you that as a function of the application, you need different devices. And this is the most important part of our power devices section of the lectures. We will study the different devices. In this figure, we again see the power on the y-axis and the switching frequency on the x-axis with many typical applications. And in addition, you can see that it is also indicated which is the typical device that we use for every application. What you can see here that there are MOSFETs at very high switching frequency. When the power increases, MOSFETs are no more used. You use something that is named IGBT modules. Then you have transistors, generic transistors. Then you have another unknown device for the moment, that is the GTO. Then you have the thyristors, the triac. Now the triac is no more used. These names are unknown for us. We will study them in the following lectures. In our lectures, we will study the bipolar transistor, the power bipolar transistor, the power MOSFET, the IGBT, that is completely new for all of you, I think, is the insulated gate bipolar transistor. This is a very important device. Then we will study the thyristor, that you probably heard of as a parasitic device in some previous lecture, some digital electronics probably. And then we will study the GTO, the gate turn-off thyristor, that is also new for you. Do not worry about not understanding these acronyms and these devices. As told before, you will study them later. When we come to power devices, power semiconductor devices, these are the typical and most important names. We can classify them as unipolar or bipolar devices. On this you can probably follow me, because in the microelectronics lectures you study a lot of physics of the devices. The bipolar devices are those in which the current conduction is dictated by both electrons and holes. The first transistor is a bipolar transistor. The NPN and PNP transistor are bipolar. The most important unipolar device is the MOSFET. There the current is only driven by electrons. There are no holes in an NMOS. And then we have IGBT, thyristor, and GTO that are also bipolar devices. It must be said that in modern applications, probably bipolar transistors are no more used. We can then say that these are obsolescent devices. But nevertheless, if you work with previously an old application, it is possible that you have to deal with bipolar transistor. We will see why these are now used always less, because they are difficult to use, are not very reliable, and the performance are not exceptional. In general, unipolar devices are much easier to use. Bipolar devices are a necessity for higher power. In the low power range, you can substitute the power MOS with bipolar, and this means that the power MOS is winning on the market now. As I like to do, we will make a short digression talking about some nomenclature aspects, because often I use words that you don't know. It's the first time you hear them. It is better to understand what you are meaning with that. When I say power device module, I mean a package, a container that contains more than a single power device. It is a module. It contains more than one power device. Let's say it's a circuit built in advance and put in a package, in a plastic container. A module usually contains from 2 to 10 power devices. This is a picture that shows an IGBT module. This will probably contain 6 IGBTs and 6 diodes, power diodes. This is for traction applications usually. And this pencil here will show you which is the size of this power module. We are no more talking about very small devices. This device will weigh some kilogram, and it's very big, and is able to handle 3000, 4000 volts without exploding, and also will carry 1000 amps without exploding, probably. These screws here are for connecting the wires. The wires are not small wires just to carry the signal. These are usually bars of copper that are thick like this to carry a lot of current without a lot of power dissipation, without a lot of resistance, and with minimal amount of parasitic inductance. This is another problem. When I say discrete device, I mean a package, a plastic container that will contain a single device. This is the way you buy a single MOSFET, a single thyristor, a single IGBT. You can buy one device. These are the typical packages. The dimensions for these packages are 1 centimeter, a couple of centimeters. These are much smaller, much lower power. This is what you find in your notebook, in a power supply for a desktop, something like that. These are even smaller. These are, who studied with me the lectures of FPGA, knows about the packages, and these are through-hole mounting. These go through the board and are soldered on the other side. These are surface mount, smaller power probably. These are MOSFETs. Then it is possible that you hear about a power system on chip, or power IC. This is something very different that we will not study in detail. We will probably do a lecture at the end of the course. And this is a VLSI system that also includes some 1, 2, 3 power devices. This is the front view of the VLSI system. There is a lot of logic here. There will be probably memories, logic, CPU, controller, whatever you want. And these big blue blocks here are some power MOSFETs. Obviously, the power here is much smaller because this entire system maybe is half a centimeter by half a centimeter by side for every side, and these MOSFETs are quite small. But you can imagine now that this is a single MOSFET that is like, I don't know, 1 million times bigger than a single digital circuit MOSFET. And actually it will carry more or less 1 million times more current. And if you have, I don't know, 10 to minus 4 amps in a single MOSFET, this will go easily to 5, 10, 20 amps, it depends on the size, resistance. And these are very important as an example in automotive applications, when you want to reduce the cost as much as you can, and hence you want to integrate the controller and the power devices in the same chip. As you can see, when you think of power electronics, you can span from VLSI, more or less. This is designing a chip, like you did you did last year in Architetture Sistemi Integrati with Professor Strollo, up to carrying very heavy devices that you need screws to connect them and very big bars to carry the current. It is a very large range of applications, and if you specialize in a particular range of power, your expertise is not immediately applicable to higher power or different power on different fields. Power electronics engineers are usually very much specialized. And notwithstanding, the applications are more or less the same. The circuits are stable. There are no new circuits every day. The basic configurations are fixed, more or less, last 50 years. But the devices change. The power devices are changing, and every time you have to change also a bit the amount of current, you change the voltage. Even if the configuration is the same, you need to design the circuits from the scratch. This means that there is a lot of repetition, but also a lot of work for power electronics engineers that are always needed. It's not like in digital circuits. When you design a full ladder once, you can use it in every circuit. If you describe in good HDL language your circuit, porting this circuit to another technology is difficult, but you don't have to start from scratch. The synthesizer, the software will help you a lot. For power circuits, it's not like that. You have to design more or less from the scratch everything. Also because you want the maximum amount of efficiency. You want to tailor your circuit for the application. In very high efficiency circuits, you are working on the point decimals of efficiency. It makes a difference 95.3 or 95.4% of efficiency. If you have 95.4, you will sell your controller, your power circuits to the customer, and you are going to beat the other one that is 95.3. This to tell you what it is, which are the industries and which is the commercial value of this field. There are thousands of applications. This means thousands of different circuits and thousands of different commercialized devices. The circuits are also sold usually in millions of units. If you design a controller for a battery charger for a cell phone, these are sold in millions of units. Probably each of us is going to buy a couple of power supplies for their cell phone per year. And this means millions and millions of units. Even if the single circuit is very cheap, you are going to sell millions per month. Since the applications are so different, there is margin for a huge number of companies that are in this field. It's not like in digital high-performance CPUs, processors. There are very few companies that drive the market, because once you design a very efficient CPU, you can use more or less everywhere. It's not like this for power circuits. You need to design a particular power circuit for this notebook. Another notebook will need a different one, even if the CPU is the same. Most of these companies, there are a lot of companies that are international companies with high revenue, but there are many more small or medium companies that work in the field. This is for circuits. For devices, we enter more or less in that region where you need the semiconductor fabs. You need some facilities, even if you need cheap facilities. You don't need very small resolutions for digital circuits, so you can do everything with cheap fabs. But nevertheless, these are in a reduced number. There are not so many companies, but quite a few of them. And I don't know if many of you know that ST Microelectronics is producing power semiconductor devices. Is a producer for power semiconductor devices. I know it is much more famous for the accelerometers, the MEMS, or other circuits. But in Catania, actually, they have also a big fab, and they do design power devices. We have Infineon, Denso, Toyota, Mitsubishi, Vishay Semiconductor, onsemi. A lot of these are in the East, in Asia, but a number are also in Europe. onsemi, Infineon, Vishay has some plants in Europe, but it is originally from Asia. Circuit manufacturers are not listed here because there are many of them. What are we going to study? We are dividing our lectures into two fields, and let's say three because the lab is not listed here. We will discuss and study the main circuits for power electronics. Then we will also study the different power devices to understand their limits and their range of operation. The topics, more or less in this order, will be power amplifiers. We will study operating class A, B, and D. We will discuss the concept of power conversion efficiency and power dissipation. Then we will study the AC-DC converters, that are the rectifiers that take an AC, an alternating voltage, and provide an output that is a constant voltage. We will study alpha and full bridge rectifier, diode ratings, capacitance and inductance filtering. Then we will study the DC to DC converters, circuits that will convert a constant voltage to another constant voltage of different value, actually an unregulated input voltage to a regulated output voltage that is constant and will not vary in time. We will study the circuit schematic, principle of operation, transfer function. We will talk about filter and ripple, how to build them with actual power devices. And we will discuss about efficiency as a function of current and frequency of operation. And some detail will be given also for the driving circuits. We will also study the isolated DC-DC converters, flyback and forward, circuit schematic, principle of operation, input and output transfer function, the snubber circuits that are ancillary circuits for power electronics, but they are very important, working principles, some examples of circuits and how to design them. And also something will be discussed about DC to AC converters that are the inverters. We will study the power dissipation that is very important for the devices and the efficiency of the circuits, static power losses, thermal characterization, thermal resistance, thermal impedance, definition and modeling, and packages. Then switching power losses for resistive and inductive load switching, snubber circuits, turn on and turn off snubber networks. For the devices, we will study the power diode that will be named PIN, that stands for P anode, intrinsic region, and cathode. And we will study the breakdown, the junction termination, the IV curve, We will discuss about generation and recombination lifetime, the dynamic behavior of the diode, and fast recovery diodes. Power bipolar junction transistors, the structure, current gain and quasi-saturation, emitter crowding, thermal instability, maximum rating and voltages, and the safe operating area. That is an important concept for every power device. For the thyristor, SCR, and GTO device structure, IV curves, turn on and turn off dynamics and gain, and the GTO structure. Some lectures will be given and dedicated to the power MOS structure, IV curve, the on resistance, planar and trench power MOSFET. We will see the structures, the voltage rating, the inductive load switching, testing for reliability and ruggedness, and the safe operating area. Finally, the last device that we will study will be the insulated gate bipolar transistor, the IGBT, device structure, output IV curves, non-punch-through and punch-through structures, inductive load switching, testing and reliability with unclamped inductive switch and short circuit, and the safe operating area. We will then conclude our lectures talking about new materials, because most of the devices are made in silicon, but it is also possible to use different materials that have possibly better performances. We will discuss about the superjunction design technique, that is an important design technique for power semiconductor devices. And if we have the possibility, we will have two lectures given by hosts by the University of Cambridge, and one will be on lateral power devices, and the other one will be on gallium nitride power devices. These students are actually they are doctors, finished their studies a long time ago, but they work in Cambridge. They are Italian, however. They started from here. They conducted their PhD in Cambridge, and one of them actually worked on lateral power devices, and the other one on gallium nitride power devices. And if we can, we will have them here to give a lecture. As I told you, we will have lab work. There will be the SPICE simulations. Important, will help you in understanding the behavior of the circuits. We will use LTSpice 4. You can download the software for free at linear.com. And if we have the possibility and I'm fit enough, we can also conduct some experiments using some demo boards with DC-DC converters. They are very, very nice, and I hope we can do that, because it's nice for you to see an actual circuit working, change the voltage, the current, measure the efficiency, and it is a lot of fun working with the electronics in the lab. Let's see if we can do this this year. Last year we were able to do a couple of lab sessions on this. I would like to increase this number. Let's see. As I told you before, the books that you can use as a reference, most of the things you will find them on the slides, and these lecture notes and the slides should be enough for the final examination. But the reference books that are very important in these fields are Baliga Power Semiconductor Devices, where you'll find everything about power devices, but only devices, not the circuits. And then we will have the Mohan Undaland Robbins, an important book on entitled Power Electronics. and it will present the power electronic circuits. They are very important books, very well written. What they miss is what we do in these lectures. Baliga just presents the power semiconductor devices and says, this is the most important thing, we will study the power devices. Mohan, on the other hand, just studied the power circuits and says the switch will be a power device. But let us imagine that this is an ideal power device. Will switch on and off immediately, it has no on-state resistance, it is an ideal device. Let's say the reality is in the middle. The power circuit defines its performance as a function of the power device. And the power device cannot be designed without having in mind the application and the circuit. And in these lectures, we try to merge these two important aspects. This concludes our lecture. We are open for questions, and also we can take a 5 minutes break.